Okay, it's 2 o'clock. Welcome, everybody. My name is Matt Hanson. I'll be the moderator for this last session. This has been a great couple days. I haven't been able to see everything, but I know that there's a bunch of talks that I'm going to go back and watch the video for, so I hope that you all have enjoyed things. This last hour, we have several talks around point clouds, but also some other miscellaneous talks. And first up is going to be Howard Butler, who is the guy to come talk to if you ever have a question about point clouds. And he'll be talking about COPIC, the new point cloud optimized point cloud format, and including how to pronounce it, right? It's COPIC.
Sure. Thanks, Matt.
It's undecided. I think it's undecided, right?
Yeah, I don't know. Every language will probably pronounce it their own way, just like GDAL and everything else. Yeah, thanks for the introduction. My name's Howard Butler. You can find me on Twitter. I have a company in Iowa City, Iowa called Hobu Inc., and we've been doing open source software for point cloud data and point cloud data management for more than a decade. Our latest effort here is with the COPIC or Cloud Optimized Point Cloud we're talking about today, but we've also done a lot of work on point cloud organization with Entwine, and then of course the open source library called Poodle, excuse me. So what's kind of a reality of point cloud data? And I talked about this a little bit yesterday as well. Is it's data that's read many more times than it's written, right? And that might give us some opportunity to organize things in a certain way that takes advantage of that. How you use point cloud data, most of the time is finding what you're looking for. It's what I call, it certainly meets the definition of big data, but it's fluffy data, right? An extra point, loss of a point in a million point cloud really has zero meaning. And the applications don't often need all of that information to be able to make decisions with the data. Open formats like LAS and LAZ have pretty good industry interoperability, but there's closed formats that can certainly do more. And up until we developed Cloud Optimized Point Cloud, there wasn't really a single file container format for doing point cloud data in a cloud native geospatial way, and that's what we're doing with this today. What got us here? Why did we want to develop this? We see this curve all over kind of society these days, which this is a plot of the linear mode LiDAR pulse rate. And that corresponds directly with resolution. And so as the sensors are increasing in resolution, the data volumes are following suit. And so the data storage, data organization, data transmission, data compression approaches that we had taken and just constructed in the early 2000s need to catch up to this. So what would be an ideal point cloud format? A grab bag of requirements, some of them certainly in conflict. Storage efficient, obviously, with fluffy data, we want to compress it, but we also want to be able to search and get what we care about. A single file has a lot of desirability for data federation and moving data around. This organization needs to support every possible computing challenge. Maybe we want to transact data as a database and keep track of what's been going in and out of it. In cloud native geospatial, being a usable thing over the network is super important. And then of course we want everyone's software to be able to read it. This thing doesn't exist, right? Like these things are all in conflict, so let's make a new one, like we tend to do. But what's missing in open formats really is this idea of spatial access and resolution selectivity. So if we drop out some of these requirements that might be in conflict, can we construct something that would meet most of these challenges? So a guy named Martin Eisenberg developed the LAZ zip software and the LAZ format. It's an adaptation and compression of ASPRS LAS. Martin, released this as open source in 2011 and 12. He was instrumental in developing LAS versions as well. And with his LAZ tools software, both commercial and open source software, had a great impact on the industry. He recently died this past September, but the LAZ's impact is certainly going to continue to be felt across the industry. So what's some thumbs up for LAZ? The first one is, at this point, except for one of the really large GIS vendors, it has industry-wide support. Everybody can mostly read LAZ natively and do what they need to with it. It's a very efficient lossless compression. And we recently changed the license of LAZZIP to be Apache public license. And what this means is applications can embed it directly, do like a static compilation and put it in an iPhone app, which iPhone has LiDAR now if you weren't tracking. And so the ability to put LAZ and LAZZIP software everywhere and do stuff with it is stronger than it ever was before. Some downsides for LAZ though is it's kind of CPU intensive, right? It's trying to make a very efficient compression, and to do that requires a very complex compression model, and it requires quite a bit of CPU to compress and decompress it. You can certainly, if you're willing to relax that, you can do quite a bit better. It also has this sort of defect or consequence of how it was of its heritage is it grew up in supporting geospatial linear mode pulse LiDAR, which is a certain kind of point cloud data that it supposes a certain model. That old Sullivan quote about form following function is absolutely true here. And formats, no matter what they are, have to make compromises about what they're going to support or how they're going to support something. But LAZ has a very strong argument for us to augment it to add what we need to make it cloud native geospatial implementation. The first is it's undeniably the storage, archive, and transmission format of large geospatial public LiDAR. There's petabytes of LAZ content out there already. It's well established. It has open source implementations. It's based on open specifications, and cloud optimized GeoTIFF shows us a way to essentially augment an existing container format and bootstrap it to an industry in an opt-in way. So if we go and attack the two features that are missing, which is spatial access or windowing and resolution selectivity of LAZ, how might we do that? The reason why we want to do this, of course, is to be able to take advantage of partial access, right? We want to touch this data over HTTP, and we need selectivity both for applications to be able to control how they move through the content to select the information that they need. We want to be able to do that in parallel as fast as we can, or as fast as our infrastructure supports, and not decide for applications how they're going to access the content. So how do we do that with COPIC? We actually store an extra bit of metadata called an octree. It's the same octree organization as entwined point tile. And then we cluster that LAZ file according to that octree. And so LAZ files support both a kind of a fixed chunking model and an adaptive chunking model. And in this case, we're storing those as adaptive chunks. It's backward compatible with LAZ 1.4. But it only supports a subset of the data record formats. And the reason for that is to limit the aperture or the window of things that developers need to support here. This LAZ 1.4 and 678 kind of is the sweet spot, certainly for LiDAR data. And it has an open specification at copic.io that you can go read and hopefully implement without too much trouble. So what? So what can I do with this? One of the concepts that Chris was showing yesterday is we want to be able to have an application, ideally a web page, we can just drop data in and quickly visualize it. So the data format needs to be supporting visualization type access. And in this particular case, this application is using the metadata to calculate which points it needs to go select, making range requests against S3 to go fetch those, and then in some worker threads decompressing that and displaying it on your screen. This particular implementation that we developed is cesium-based and supports both the COPIC and EPT point cloud data structures as a single point kind of application for convenient visualization. You can pass in multiple resources, you can save your viewpoints and stuff like that. It also reads many coordinate systems. Coordinate systems in LAZ and LAS can be quite challenging, especially in JavaScript environment. Coordinate systems in general in JavaScript environment can be challenging. Right now it's a free resource, but we haven't released it as open source. Still talking about that. So what else can you do with COPIC? So computing an overview with the data. The ability to select for both the resolution and the window means that software applications can traverse through the data and control their traversal through the data. You're doing that with a COG file, whether you're using GDAL to select an overview or some other application, or all the fantastic browser-based visualization we saw the last couple of days is doing the same kind of thing. The ability for an application like Poodle to be able to do that means that instead of touching this file with 360 million points and throwing most of them on the floor, we can construct a kind of a quick preview image to make sure we're located where we want to be or something like that in a few seconds, and only touch much smaller percentage of the data, and do it over HTTP and get the convenience of the cloud native geospatial thing. Another important concept here that we've also seen this as cloud optimized GeoTIFF is the ability to parallelize your software moving across this data. We don't have a server in the mix other than HTTP, and the application controlling how it does that means that it can control how it parallelizes across the data as well. So what else can I do with COPIC? Pretty quick here, the release that comes in June, you can go get it now in the nightlies. QGIS is going to support COPIC for visualization and for analysis. And so, Martin Tobias and the Lucher team here have sent us along this movie that shows a COPIC file that is Melbourne, Australia, that we made available online on the copic.io website. This is great visualization. We can make some movies and stuff like that. But the real power is you have all of QGIS available to you, right? So all of the analysis, elevation modeling, filtering, meshing, all of the stuff you might want to do in QGIS to elevation content, you can do with COPIC files. And this is a really important step for making this stuff super convenient and being able to do it, local file system, but also over HTTP. The same model that has been tread down with cloud optimized point cloud, or excuse me, cloud optimized GeoTIFF. So what else can you do with COPIC? So our team has been working with the Planetary computer team as well to construct their catalog with a STAC-based catalog using COPIC to model and store all of USGS 3-depth LiDAR point cloud content. There's been a lot of talk about Planetary computer here in these couple sessions, so I won't get into too much detail there. And I have a Jupyter notebook that shows how you as a programmer can essentially touch their API, go figure out which data you're going to read, and then do Poodle stuff to it. So in this particular case, I was computing height above ground model to find that the building nearest the bean in Chicago is like 380 meters high. This is really powerful for allowing applications, again, to control how they're touching the data, only access the parts they need, and that particular window there actually covers 4 tiles. All of the sort of stack access that you would do also applies for COPIC files here. And so the processing compute model is essentially the same, except it's point cloud content instead of raster content. So what else can I do with COPIC? Well, the same thing with COG, it's just an LAZ file, right? So all of your existing workflows that are using LAZ to do stuff like LAZ tools, white box tools, maybe you're doing cloud compare visualization, they don't need to know that special metadata to be able to read the content as LAZ. And that's a really important concept here in terms of making this data accessible and not having to have a discontinuity where you're trying to bootstrap an industry with petabytes of history, essentially, of content that it can't simply convert to a new thing, not all at once. So, people have asked us, well, hey, you were doing this in 20-point tile thing. Why are you doing the COPIC stuff now? And it comes down to, for us and for LiDAR point cloud, the distinction between an exploded data organization and a condensed data organization. So in an exploded organization, depending on which cloud you're in, you might have per object access cost, and that could be quite substantial for really large point clouds with millions of objects in them. But the most significant challenge with an exploded data storage is it's impractical to move them. And so if you're in the cloud and you're always in the cloud and you're never moving data, it's not really an issue. But if you ever have to federate this data or air gap it across something or put it on someone's desktop because they don't have network access, an exploded data format is very, very difficult. You have to put it into a suitcase and haul it over somewhere and then dump it back out again. You know, this is whereas COPIC has the same pitch as COG, which is it's condensed, it's all together. It might be one file. Sometimes they could be big, really big if you wanted to, or they'll be small. And it's the data provider's prerogative to control how big or small those tiles would be. Another challenge that Ryan talked about in his talk this morning is with ZAR is that data that's modeled as a exploded is kind of like a STAC collection, right? It's a whole bunch of tiles. It's a whole bunch of different data that's all put together with one kind of semantic meaning. And but STAC's atomic unit is item. And so for better or worse, in LiDAR, point cloud tile and raster content too is kind of the dominant organizing principle. And so data that are exploded as a collection of tiles, we found them difficult to model in STAC, and being able to do this with cloud optimized point cloud is easier. And then finally, at least for the point cloud, geospatial point cloud industry, bootstrapping support for it for a new thing is very, very difficult, right? There's a lot of inertia you're pushing against. Even with EPT, where we have all of the EPT content available in Amazon Public Data Store, and it's available for people to compute there, and it's updated daily, and it's like 40 trillion points right now. The people doing that are doing that to compute in the cloud, and the rest of the industry hasn't really followed suit, right? Because it's kind of something special they would have to build into their software. Whereas something that's LAZ based, which they're already reading it, adding support for it is an opt-in thing. It's not a have-to thing. And so that pitch is just much easier for people to get on board with, and they don't have to do everything all at once. So what's the roadmap here? We finalized the spec in November of last year. And then this past March, we released Poodle 2.4, which provides both a readers.copic and a writer.copic stage. And this means Poodle application users can use that content, Copic content for analysis and take advantage of that spatial and resolution selectivity feature that Copic has. We have an open source software called Untwine, which is able to construct very large Copic files in a efficient way, exchanging memory for file storage. So it'll use a lot of cache to build things out, but you can throw most of that away. There's an open source library from a team called Rock Robotic, based on Python and C++, that for making Copic files and doing stuff in Python. Connor Manning from the Hobu team manages the Copic.js, which you saw in the visualizer being used. Lucha team has QGIS, support for Copic available in the nightlies if you are willing to hack and slash to go get that to work, to be released here in June of 2022. And then some of these other projects all have this at least on their radar or on their queue, right? So they're certainly taking a hard look at what's available and seeing what's going to happen with industry support and who's starting to pick it up. So final take homes from my talk. COPIC here is an extension of LAZ that supports spatial query, spatial windowing, spatial resolution. It's backward compatible with LAZ 1.4. The LAZZIP library and LAZZIP codebase was relicensed to Apache public license. That means you can embed this in your own commercial software, do what you need with it to provide LAZ and COPIC support for your applications. There's lots of open source support that we've helped bootstrap. Commercial support hopefully coming. Ask your software vendor for it. Show them all the stuff that's available. And finally, there's no official pronunciation. We're calling it COPIC at our office, but as long as everybody knows what you're talking about and you're able to communicate what's going on, good for you. So thank you very much.
Thank you so much, Howard. That was great. Great learning more about the format. I don't see any pressing questions, and to make sure that we have enough time for everybody, there's a bunch of talks to get through. We'll move on, and if any questions pop up, Oh, actually, there is a question here from Brian Hamlin. Can LAZZIP ship in Debian after relicense?
It should be able to, yeah. I mean,
I
the
guess so,
Debian
right?
team
Because
was,
it's Apache now.
yeah, the Debian team was actually the ones who helped work through some of the licensing issues that LAZZIP had originally. And so, you know, with the code-based relicense, it shouldn't be any sort of issue there at all.
Awesome. Well, thanks for that, Howard. Great talk. All right, next up we have Darren Weens. Wait, did I pronounce that right? Is it Weens?
Yes, Weens.
All right, I should have known that, but I guess I did. So Darren's going to be talking about extension for representing video in STAC. Take it away.
Yeah, okay. Thanks. I'll assume that you can see my screen. Just yell at me if you can't.
Yep, no, we're good.
Yep, so I'm Darren Weens, a geospatial developer at Spark Geo, and I'll be talking about a new STAC extension for video assets. Yeah, so I made this animation in Blender and I'm very proud of it, so don't tease me in Gitter. But the intent of the extension is to describe all different forms of overhead video assets, whether it comes from a drone or airplane or satellite. And in addition, it should support both a moving sensor. So if the actual vehicle is moving, should support that, and also support a moving and dynamic frame area. So it can, like the actual shape of the rectangular video being collected should be able to be described in the metadata. So most of the new properties are at the item level. So you can fill in the pixel dimensions, and then things like frame rate, frame count, and then video specific properties about video codec and whether there's no data letterbox areas around your video, and then some well-known sensor identification fields. I also include some suggestions for assets to include in your items. So you should always have a video asset that points to the actual video file, but then you should also have a frame geometry asset, which would be a GeoJSON polygon feature collection indicating the four corners in geographic coordinates of the video, as well as the frame center coordinates and the sensor coordinates. And if you combine all of those geographical assets together, you should be able to make sort of an animation like you see on the right here, where there's the sensor points are sort of orbiting around the rectangular video frame coordinates. I'll just warn you now that the next slide is a little bit crazy with 3 videos all playing at the same time. So if you're prone to motion sickness, you might just want to look away or just be aware. So here's an example of full motion video that this STAC extension would apply to. So on the left is a seemingly aspatial video that's taken from a helicopter that follows a truck on a highway. There is embedded geographical metadata that's stored as in-band metadata right within the video file. And if we extract that in-band metadata out into GeoJSON features, we can then make like a UI on a web map that takes advantage of those frame corner coordinates, and also in the top example, I've locked the camera to the sensor coordinates, and in the bottom, the camera is free floating, but both of them are using the same UI in Mapbox, or you can do this in MapLibra or other UI. There is a full example on the SparkGeo blog that shows how you can actually extract the in-band metadata from certain video files. So you can find that at the URL here. And thanks to Brad Hards, who's provided a lot of useful feedback on the extension so far. I'm still accepting more feedback on the extension, so please go to the GitHub repo to provide that through either issues or discussions. Thanks to the STAC community for being so welcoming and helping me make my very first STAC extension contribution. And that's it. You can find the extension repo here and find me at Twitter to talk more about it.
Awesome. Thanks a lot, Darren. I do have some questions. I'm glad that you went through this because I hadn't really looked much at the extension, but we don't have time. And so either we'll have time at the end or I will comment on issues in the repo after this. But yeah, very cool.
We can talk more about it on Gitter or GitHub, wherever.
All right. Yeah, sounds good. Sounds good. All right. So next up, we've got Kurt Schweer from Google, who's going to be talking about STAC and Google Earth Engine. And I will give you a 1-minute warning because I was looking and we have actually quite a bit of talks that will no way fit into the hour, but we can at least try and keep as close as we can. So, all right, Kurt, it's all yours.
All right, let's see if I'm sharing my screen. I don't see anything. Did I do that wrong?
Yeah.
Let's try again.
Well, I can see.
There we go. All right. So today I want to talk about STAC and the Google Earth Engine. This is going to be just a taste of it, so it's pretty quick. And let's jump into it. So Earth Engine is a computation platform that takes all of your desires in code and parallelizes them and gives you back some results. It's pretty powerful. You can do lots of stuff with it, but computation needs data. If you don't have any data, your computation is probably not very exciting. So we have a public data catalog with a bunch of data. It's 50-ish petabytes, 600 data sets or so. Lots of cool data to work with. But if you can't find it, that's also a problem. So users need a way to see what's in there, and that's a catalog. So Earth Engine's had a catalog for a while. You can search for it and group things. You can say here, find things tagged ocean. And to give a quick history of Earth Engine, it's been around since 2009. About 2018 is when we had our first catalog available for users. It was launched. And in 2019, we had our first release of a STAC catalog. It was derived from an internal proto-based catalog. So it was basically just taking the protos, turning them into STAC, and then shoving them out on a bucket on the cloud. In December of last year, we turned things around so that we now have a directory of STAC content, and that STAC content drives our catalog. And when we need protos, we derive them from STAC. So we are now based on STAC. There's a bit of a mapping problem that we had to go through. Earth Engine has a bunch of its types. STAC has catalogs, collections, and items. We ended up with all of the Earth Engine data sets mapped directly just to collections. So we have catalog files for people to use, but we don't use them. We just focus on each Earth Engine data set is a STAC catalog, or sorry, a STAC collection. And we stick those files on a GCS bucket. And what those look like is a bunch of JSON. So here we've got an example. I don't expect you to read any of this, but basically it just shows you what's going on with the contents, and it's all the stuff you'd expect with STAC. We needed to be able to scale this and be able to edit it and maintain it. And so we wanted some sort of templating system to help make our lives easier. And there are lots of ways to slice this. You can write more JSON just directly. You can glue together stack catalogs across different organizations. You can do various generic templating approaches where you blend like Python and Django and Jinja or something like that. You can use databases and drive that with templating. You can then do things like take templating languages that are designed for JSON, where it might be a little bit closer together. You can choose your own adventure. You can mix and match lots of those different options. We decided to go with something called JSONit, which is very close to JSON. And it's actually, you can take a JSON file, drop it in as a JSONit file, and it actually works just as is, or you can get a lot fancier. And the nice thing about JSON is it's a complete language. It's Turing complete for those of you who care. You can write functions, do all sorts of stuff, and out the other end comes your JSON that you would like to have. So here is
1 minute.
Yep. Okay. We have some helper files that we can build. We can have things like your stack version. You can have your Earth Engine helper functions that say like your extent, things that you generally want. You can then have a catalog entry that's got a bunch of local variables you're going to fill into your template in the same file. Then you can use those to write out what you want to have in your stack. And then you can have out the other end from that template come out the stack JSON that you'd like. There's the rest of it. And from that, you have a stack catalog and you have the original Earth Engine catalog that most of our users use up till now. You have the best of both worlds. So that's my talk, and thank you for listening. The slides are available at the link below. And feel free to talk to us. We'd like more feedback on Stack and Earth Engine. Thank you.
Awesome. Thanks so much, Kurt. Yeah, Google Earth Engine, I use it as an example whenever I'm explaining cloud native geospatial, because it really was like the first cloud native geospatial infrastructure, really, that now all these other systems are essentially trying to do, doing the same thing with open source components. So yeah, really cool to see the use of Stack in there. So thanks again.